Last week when we talked about op amps, we said that you could think about the internals of an op amp as behaving kind of like this equivalent circuit. So a circuit where there's some resistance that connects together the input terminals. So we'll call this Ri for the input resistance. And a dependent source, a dependent voltage source, with a voltage which is equal to a parameter A, which is called the open loop gain, multiplied by the difference in voltage between our terminals, so Vp and Vn as the voltage at the positive and negative terminals respectively. That this dependent source would then go through a resistor, right, which would be basically the Thevenin equivalent circuit of this source, and that this would be a more realistic description of the internals of an op amp. So let's use that to actually go and analyze a particular amplifier, so our good old friend, the inverting amplifier circuit. And we're going to analyze this using our more realistic model. So this is a model we can always use. So we don't need to check for negative feedback, and we don't need to make these assumptions. We can actually just draw the more realistic circuit and analyze it directly from that. So let's go ahead and actually do that for this particular system. So I have a voltage source, which is our input. That runs through a 10 kilo ohm resistor, and it goes to my op amp. So then inside my op amp, there is a resistor that connects together these terminals. So that's the negative and the positive, or the inverting and non-inverting terminals. And then out of the non-inverting terminal, well, that's grounded. And also would connect back to our source, our VI source. Okay, we have elsewhere, looking at the output stage of our op amp, we have the voltage-controlled voltage source, and we know that that is related to the voltages at these inputs. So this was Vn, and this one here is Vp. So we have Vn minus Vp, and it runs through a output resistor, like so. Now we can go and find a real op amp, like an actual physical product, and we can go and get some values to put into this particular circuit. So what I have here is the data sheet for a family of op amps created by Texas Instruments. So I'm looking at LM258, LM358 are like sort of standard models. And in the data sheet, so this is the information that the manufacturer provides for people who are going to use these op amps, there's a whole lot of useful information. So I'm just going to scroll through and highlight some of these things. So first of all, there's this pinout diagram, which explains how to physically use the chip. So it's a little chip, right, with 8 legs, and you wanted to put this on a breadboard, you have to know how to use it. So the way to understand this diagram, we've got input terminals, which are labeled as negative and positive, so they are the inverting and non-inverting terminals, and those connect to an output. So basically that is kind of one half of the chip. And this particular chip actually contains 2 op amps. So you get another one over here, and it connects to this output 2 here. And then, of course, there's the power supply rails. So the power rails are pins 4 and 8, respectively. So there's a positive rail, V plus, and a negative rail, V minus, and those are shared by both of the op amps on the chip. So that's how you would actually use the physical part, assuming that you have the one of these packages. So here's all the names of the different types of packages, which are the ones that look like this. And then, of course, there's another package in which you can buy it, and you can read about those pins there. NC means not connected, if you ever see that. It's basically not used. Then we come to absolute maximum ratings. Basically, these are values that will destroy the chip if you ever exceed them. So depending on the exact model number that you have, there are sort of different maximum voltages that will cause damage. What they mean by this here is that if you had dual supplies, so plus or minus 16 volts, that's the absolute maximum. Or if you have a single-ended supply, so 32 volts and ground, in both cases the difference, the total supply voltage, would still be 32 volts. So that's how you understand that terminology. But absolute maximum ratings is basically what do you need to not kill the thing. That's probably not where you want to be operating. What you really want to do is look for the bit where it says recommended. So these are the circumstances under which the device will be well behaved. And so here you can learn about the voltages that you can use and so on. But for our purposes, we're trying to actually model these op amps. So let's have a look at the electrical characteristics for the LM358B. So suppose this is the chip that I have. There's a few parameters here that I can extract and put them into the circuit model that I'm using. So for example, input impedance. So impedance is similar to resistance. For the purposes of this subject, you can think of it as the same thing. So we have that the differential input impedance is 10 mega ohms. So I can go back to my circuit diagram and I can label here 10 mega ohms as the input impedance. All right. I can also identify the open loop gain to be, by the way, in these columns, they have minimum, typical, and maximum. So I'm just going to look at the values in the typical column. So the typical open loop gain is 140 volts per millivolt. So what they mean by that is if there was 1 millivolt of difference across, so that unit means if there was 1 millivolt of difference, then there would be 140 volts generated by the source. So let's go back to our picture. If I have 1 millivolt of difference over here, then I would have 140 volts being generated by my source. So you see this is quite large. So I actually have here that my value of A as a dimensionless quantity is going to be 140,000. So that's the kind of relationship from volts to volts would be a gain of 140,000. And I also need to know the output resistance, and that is also specified just here. So the output resistance, R0, is 300 ohms. So I can write here on my circuit 300 ohms as the output resistance for this thing. So I've now kind of labeled the internal workings of this op amp. I'm just going to move that over a little. I haven't drawn the feedback path yet, so there was also a feedback resistor that will connect into here, and the feedback resistor in our circuit is 20 kilo ohms. Our output is this one here. So now I have a complete circuit with all of the information that I need, and I can go and analyze it. So without making the assumptions that I previously had to make. So let's go and have a look at that. How will I go about this? Well, I'll use node voltage method, and I will write KCL around this particular node here. So Kirchhoff's current law at Vn, and here's how that is going to look. So the currents leaving to the left is going to be Vn minus Vi divided by 10,000. The currents leaving through the op amp will be Vn divided by 10 mega ohms, so that's 10 by 10 to the 6. And the current leaving through the feedback path is going to be Vn minus V0 divided by 20,000, so 20 kilo ohms. And that's equal to 0. So what I'd like to do here is analyze for the output voltage. So Vn is kind of an internal value that I don't really care about, right? The thing that I'm actually trying to analyze is what's the output voltage as a function of the input. So I want to eliminate it from my system of equations. So I'm going to solve for Vn in this case. So solving for Vn, I will get, so I'm going to just collect some like terms over here. So this one will give me factor of 1 on 10,000. Then I will have a factor of 1 on 10 to the 7. And last term is a factor of 1 on 20,000. So all of that multiplied by Vn, and then I look at the other terms that I have. They will be minus Vi over 10,000 and minus V0 over 20,000, and that is equal to 0. All right, so we can use some, or we can just calculate these values, right? So the thing in parentheses at the front there, I'm just going to type all of this in to my calculator. 10 to 10 to the 7, so that's 10 million and 1 over 20,000. And so I end up with 0.000151 times Vn, and some other numbers over here, so I'll just write them with the fractions for now. The 20,000 is equal to 0. Okay. We can multiply everything by 20,000. That will clean up these fractions. So if I just take that previous result, multiply by 20,000, I'm going to get 3.002 Vn minus 2 Vi minus V0 is equal to 0. So therefore Vn is 2Vi plus V0 divide 3.002. All right, and we'll call that equation number 1. All right, looking back at our circuit, I can also analyze the output node V0, and so I can write KVL at that node. So KVL at the output will look like this. KCL, I should say, KCL, Kirchhoff's current law, at the output is going to look like this. So the current leaving to the left is V0 minus the source. So the source is going to be A times, well, Vn minus Vp. Well, Vp is 0. Vp is 0. So I will just write Vn. And that is divided by the output resistance, which was 300 ohms. Okay, then I have the current in the feedback path, so that one is V0 minus Vn divided by 20 kilo ohms. And that equation is equal to 0. Now I can substitute in some values that I know. So I have a value for my open loop gain. So it's 140,000. So let's write that. V0 minus 140,000 times Vn divided by 300 plus V0 over 20,000 minus Vn over 20,000 is equal to 0. All right, let's bring our terms involving Vn together so I can substitute them in easily, and also my terms involving V out together, so that will leave me with 1 over 300 plus 1 over 20,000 is the output voltage there. And then the terms involving Vn, there's a negative 140,000 divided by 300, and a negative 1 on 20,000. Vn is equal to 0. I can substitute from equation number 1, and I might as well clean up some of these numbers as I go. So that first set of brackets there is, bear with me, .0.0033833 like this. I'll keep a few significant figures for now. Then the numbers in the second bracket are, let's write them in, so that's negative 140,000 divide 300 minus 1 over 20,000. So this would be negative 466.6667 times Vn. I was substituting for Vn, so let's take Vn, which was 2Vi plus V0 divide 3.002, and that is equal to 0. All right, we're pretty close to the end here. Let's bring together all of our terms involving the output voltage. So involving the output voltage, we have this small number at the front, and then a minus 466.66672 divide 3.002. So all of that is our coefficient for the output voltage, and then our coefficient for the input voltage is going to be 466.66672 times 2 divided by 3.002, that is times Vi, is equal to 0. All right, let's calculate again. 338,333 minus 466.66672 divide 3.002. So this leaves me with minus 155.446 V0 minus, so 466.66672 times 2 divided by 3.002 is 310.9038 Vi is equal to 0. So we are nearly there. If I bring my, I'm going to swap my signs, right? Multiply everything by -1 and it becomes positive and positive. And then I can take my Vi to the other side. I'm solving for V0 and divide through. So it's going to be V0 is negative 310.9038 divided by 155.4486 times Vi. And if I take that, divide 155.4486, then the answer that I get is 2.00004 times Vi. Okay, so it's very, very close to our ideal gain of 2. If we go back and look at our circuit, we have an inverting amplifier, and we know that the gain is feedback resistor, which is 20k, divided by source resistor, which is 10. So like ideal gain is negative RF over RS is negative 20k divided by 10k equals 2. And then when I analyzed this using our more realistic model, and I went and picked actual numbers from a real op-amp, then I ended up with a really, really close value down here. So very, very close. I should have a minus sign. I dropped a minus sign in going from here to here. So very, very close to the expected value. So you can see that the assumptions that we've been using are actually pretty good, and real op-amps behave pretty close to the ideal expected behavior. But the advantage of this strategy is I didn't need to assume that negative feedback path, right? I can use this model for any op-amp circuit, right? This method will always work, whereas the previous methods only apply under special conditions. Here I can always use this particular strategy in order to analyze it.